Welcome back. Dig these fine threads. Today we start threads, hence the joke. These are today's topics, and here are the chapter objectives. So threads are a facility, an operating system facility available to applications. You've probably already written some threaded programs. As listed here, there are multiple reasons for using threads. We say process creation is heavyweight. Remember, there are a lot of resources that have to be set up to run a process. So specifically, the fork system call takes a lot of time setting up the resources for the process and getting it going, whereas thread creation, we say, is lightweight. The only resources that the thread needs are essentially the activation frame stack and a set of variables and some scheduling information, which may be kept down at the user level or the kernel level, as we'll see. These days, kernels are multi-threaded. That means that multiple threads can be executing in kernel mode at the same time, which implies multiple locks, which is something we'll talk about later. But once upon a time, kernels were single-threaded, which meant that only one thread could be running in kernel mode at a time, and that was a serious bottleneck. For this example, let's assume again that we have a web browser for the client and a web server for the server. The server starts off as a process. When it receives a request, it creates a thread to handle that request. And remember, because threads are lightweight, that can be done quickly and efficiently, and then the server itself goes back to listening for other requests. All right, in terms of these benefits, I want to point out a few things. Under responsiveness, if one thread is blocked waiting on I/O, the other threads of the application can continue working. Depending upon which threading model we'll use, as we see later. Let's see, under resource sharing, well, threads are all working in the same address space, so global variables are automatically shared. There's no reason to set up the shared memory that we saw earlier with processes, and there's no need for message passing necessarily. Threads, as we've already talked about, threads are easier to set up, and also context switching between threads is inexpensive in a relative sense. And then finally, for a single application to take advantage of today's multi-core, multi-processor systems, threading is a natural way to take advantage of those additional CPU resources. Multi-core programming is a pretty large challenge. Here you can see some of the problems. How do we divide the tasks that must be performed within an application? Similarly, how do we divide the data to be processed? How do we balance workloads? How do we synchronize the various threads so that we obtain correct results? And then finally, with all these different threads of control, how do we test and debug? Here you see the definitions of parallelism and concurrency. Just thinking about CPU cycles, parallelism is only achieved in a system with multiple CPUs, which imply that more than one task can actually be executing simultaneously. Concurrency is the notion that more than one task can make progress. So the concurrency is possible on single core systems in which the CPU scheduler multiplexes between the various processes. So the execution of the processes is interleaved rather than the first process running to completion followed by the second process running to completion, etc. So an example of data parallelism would be an image processing program. The image data, it's an image, so it's a 2 by 2 or a two-dimensional array of pixels. That pixel data, let's say we have 4 cores, could be split up into 4 regions, and then each core takes a region. Task parallelism, again, go back to the server example. You have one thread performing the listening operation, and then other threads that handle the requests. So with respect to hardware threads, Intel, for example, has the feature they call hyper-threading, in which you have a single execution pipeline, but 2 different sets of pipeline registers that allow 2 threads to be interleaved in execution through the pipeline. So here's a figure illustrating the differences between concurrency and parallelism. See, in the concurrent execution example in a single core system, the tasks are interleaved. So T1, T2, T3, T4, T1, etc., etc., etc. Obviously, at any one time, only one task is executing, and then parallelism on a multi-core system, which again, within a single core, we have concurrency, but because we have 2 cores, we have parallelism. Here you can see the resources dedicated to individual threads. On the left, the traditional process, and the thread resources are the registers and stack, and then the process or the remaining resources are the code segment, the heap segment, the data segment, and files and other I/O resources. And then on the right, a multi-threaded process. You can see that each thread has its own execution stack and its own set of registers. So when adding or when creating a new thread, all we have to allocate is an execution stack and storage for the registers when the thread isn't running. So as stated here, Amdahl's law says that the serial portion of an application has a disproportionate effect on performance gain by adding additional cores. The weakness in Amdahl's law is that it assumes that we keep running the same program on the same data set. What adding cores can help with is scaling the problem to larger data sets. Amdahl's law doesn't account for that. So, for example, if we have a weather forecasting program that we run for a single state, a single state of the Maryland, if we add cores, we might be able to run the same simulation in the same amount of time for more states, say the entire Mid-Atlantic, for example. User threads are managed in user land by a thread library. The kernel is unaware of them, and that has implications that we'll see shortly. Kernel threads supported by the kernel, and the thread or the kernel is aware of kernel threads. In each of these 3 models, we're talking about a mapping between user threads and kernel threads. So for instance, in many to one, we are mapping many user threads to one kernel thread. All right, so here's the many to one model, in which we have many user threads mapped to a single kernel thread. And in this model, the user threads run concurrently. So they'll never run in parallel, although of course there could be other sets of user threads running on a different kernel thread. And if one thread blocks due to, say, I/O, they are all blocked. With one-to-one threads, we have one user thread per kernel thread. In this model, if one thread blocks, the others can continue working. And if there are multiple cores upon which to run the kernel threads, then the user threads can run in parallel. Otherwise, they'll be running concurrently again. And then finally, we have the many-to-many model here, in which we have many user threads that are mapped onto many kernel threads, and the user threads are multiplexed among the kernel threads, and a user thread could potentially move from kernel thread to kernel threads, and if a user thread blocks, a kernel thread will block along with it, while the remaining user threads will multiplex on the remaining unblocked kernel threads. So here's the two-level model is a hybrid model in which a user thread can be bound exclusively to our kernel thread. Well, that finishes this first three sections on threads. I have to admit that threads joke that I opened with was pretty weak. You might say that it was threadbare.